2y. So that's 1/4 of 1 plus 2 cosine 2y plus cosine squared 2y. And then that you break into 1/2 of 1 plus the cosine of 4y. And at that point, everything there you can integrate, and you're done. So it's just like integrating cosine squared, but you do it twice. Yeah. Oh, I just said solve. So the default for solve is the implicit general solution. Oh, you tried to solve for y?
Yeah, and I was like, this is impossible.
Yeah, it's impossible. I would agree. Yeah, pretty much.
Yeah, I just looked at that. I was like, I ain't solving
And so there in a nutshell is why I would argue that the more natural concept for solution is probably like implicit solution, because almost every problem you can find an implicit solution for, but very few problems we can find a explicit solution nicely. Do you guys have any other questions? We can talk about the mission. I have a few minutes. Apparently nobody else is in here. On the mission 4? I haven't solved those yet, but I'll try.
The second to last one, 139, I don't think it's worth it. Because that's one of the useful.
I actually like problem 124. That one was fun, wasn't it? It's neat how much different variety is in that one equation. Did you like my problem 123, Vince? I spent a while constructing these.
Oh my gosh.
They're cool, aren't they? Yeah.
This is literally, I almost thought that my calling was
Problem 126 or something like it makes a fantastic final exam question, because it's like geometrically very clear. And if you're just mindlessly following formulas and not thinking for yourself, this problem becomes very difficult. I often like to ask a question like this just to see if you're thinking. But I don't know, there's also things, for the same reason, it's a bad question. Cardioid makes a nice example. It's hard to find an example where both the area integral and the arc length integral are both like nice. What's one that you can do both the area and the arc length integral for? What's that? A single point. How about a circle? Circling bad. Let's see, here's that example again. Hey, look at that. Oh, I'm so boring. I guess this on the quiz too? Oh, but it had 3 petals there, right? Yeah. Let's see here. That one's a nice problem. Oh, this I wanted to talk about a little bit. So problem 132, there's a right and a wrong way to do this. The right way to do this is with thinking. And if you're thinking, you should be able to see, wait a minute, this is nothing more than y plus x equals to 1, otherwise known as y equals to 1 minus x, which means we're looking at a triangle. 1/2 base times height. Right. So no calculus. It's just triangle, right? But if you insist on using polar coordinates, you can do that. And in fact, you can write the sine plus the cosine as √2 times the sine of theta plus pi over 4, which you can easily check is right. You might wonder how you derive such identities as that. The answer is by phasors. The phasor method, yes, which is what I show down here. It's not a Star Trek. It's an electrical engineering usually. But anyway, so yeah, with that trigonometry, then I can do the integral and get a half. But this is obviously the wrong way of doing it, right? This speaks to a deeper truth, which is that you should solve problems in their natural coordinate system. The natural coordinate system for a triangle is like Cartesian coordinates. Triangles belong to the world of Cartesian coordinates. Circles, on the other hand, belong to polar coordinates, right? So the area of a circle, easy with polar coordinates, difficult with Cartesian and vice versa. So here's take it or leave it. Here's a way to, this is not part of the required content of the course, just to be clear. But if you're interested in deeper trigonometry, this is how to manipulate yet another, if you have sines and cosines of the same angle, you can look at them as like real or imaginary parts of imaginary exponentials. And then if you're adding imaginary exponentials of the same argument, then you can just like factor something out and find its polar representation. And so that allows you like this calculation, which then is nice because this is just a sine and a cosine at theta plus pi over 4. And then if you like equate the imaginary parts of these things, you can derive the identity. If you don't understand what I'm talking about, it's fine. I'm really just including this for your later reference, okay? I think this is a good example of the one I muddled in the last battle, the final battle. Who said last battle? Somebody's got me on the last battle. It's all your fault, isn't it? My brother's been reading Miracles lately. He's talking about how much he loves Miracles. Another C.S. Lewis book. I think we do. Yeah, there is a... I hope you understood problem 135 and 136 were more for breadth, but the point of this was to explore the perpendicularity in some sense of the polar coordinate frame, that unit vectors in the direction of increasing r and theta are perpendicular, is what this works out. In contrast, if you come and take Calc 3 with me, we'll talk more about this, but not this part, but the theta part, r theta part. On the other hand, if we look at a hyperbolic coordinates defined like that, it doesn't work out nicely. Like you see the h hat and the beta hat, they're not usually perpendicular. But I don't know. I did a bunch of algebra. I figured out that the angle between them is inverse cosine of the hyperbolic tangent of twice beta naught. I don't know. It's something. This one, I like this one. This one wasn't bad. That one was also in your quiz, right? This was the one I also put on your quiz, right? 1 and -1. This one was nice. It made sense to me. Only the odd coefficients survived and all the evens were 0. But I got to tell you, I wonder about my answer to this one because it's just very unsettling to me. I worked it out and I got that the odd cosine coefficients were that. The even ones were 0. But in contrast, the sine coefficients, they're all non-zero. It's very lopsided to me. It feels... Did you guys get this? It was weird? Okay.
Yeah.
It was just kind of lopsided. I don't know, it was just kind of weird, but anyway. Do you guys have any questions about previous tests? I mean, I would encourage you, like as a starting point of studying, just go back and look through, like, what are the problems we did on the missions, glance through those, you know, what, obviously look at your notes. I would look at the old math battles. I would look at the old, of course, look at the tests and their solutions, right? I try to look at all those things as I'm making the final, as a general point of order. I should tell you at least one thing that's not on the final, right? I will not put problem 1 of test 1 or anything like it on the final. Is it too easy? No, it's just I'm going to, you know, that's Calc. I will revisit that in Calc 3 forever. I mean, we have 2 hours, and that's not really the central point of this course. I was doing that actually primarily as a favor to you guys. Yes. Yeah, I don't want to take points off because you guys can't find standard. Well, but I shouldn't say that because the standard angle thing comes up again in polar coordinates, right? So when I say I won't do this, I mean literally I won't do this. I don't mean I'm not going to test on polar coordinate standard angle. I can't rule that out. That would be incorrect. So you guys ready to integrate by parts? I think so, right? Partial fractions. We haven't done surface area in a bit. You might want to, brush up on that. See here. Yeah, want to look back at the triangle for the substitution.
This one, I didn't get even though it was so easy. It's frustrating. I walked out.
I'm still mad about the question that I said that tangent of something was, I think like the limit of tangent, of inverse tangent was like pi over, I said it was pi over 4.
I think you guys did pretty well on test 2, if I remember right.
Yeah, but I didn't get the first part.
Yeah. Those definitions still matter. I mean, there's 2 definitions we need to know carefully. Definition of the limit of a sequence, right? And the definition of a series, right? Like not knowing definition of series clearly made solving that problem 17 on the final battle more complicated than it needed to be. If you really understand the definition for series, problem 17 should be a piece of cake on the final battle. But anyway. Of course, we've got all the convergence, divergence tests. A lot of you did problem 4 a wrong way. A lot of people got credit for problem 4 here, but didn't do it in the sense that you should have done it, if that makes sense. So the idea here was to use geometric series to see something, and you guys used a lot of anything else, like just plain old tinkering, middle school style or whatever. And I can't fault you, but there you go. So I'll try to work out the problem like this on the final battle. So you have another example there, like this. Oh, telescoping series. Again, really understanding telescoping series become easy if you really understand the definition of series. What's the partial sum versus what's the sum of the series? How are these related? With a telescoping series, we can find a formula for the nth partial sum, which means we take the limit to get the sum of the series, right? Alternating series are nice. I do usually try to test on the alternating series estimation theorem somewhere. It's usually most interesting to ask a question like integrate this function and approximate it to a certain thing, because that allows me to test the first couple terms idea in power series at the same time I'm testing something else. So it's like one problem takes care of a couple of different things. And I think it's usually the case if a person's weak on one of those topics, they're weak on both, so it doesn't kind of, anyway, I try to, I'll shut up. Problem 6 has got a kind of delicate limit that not all of you learned. So I think a lot of you probably need to revisit part C here. It's easy to let that slip past you. Problem 7 is problem 17 on the last battle. It's the final battle question all over. It's the same thing, pretty much. And problem 8, you guys destroyed this question as a class. Like, you guys did really well on this. So I probably will come back to that, because I should ask something like that. I like problem 9. You guys didn't get problem 9. Yeah, what's a flirkin? I don't want to talk about this because I haven't seen Endgame yet, and I'm afraid that talking about Flurkins will not be helpful. It might tempt you guys to just tell me soon. 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 Could a Flurkin ingest a Divergent series, but have room in its stomach? Discuss. Yes. Anyway. Well, I think that's it. Do you guys have any other questions?
I have a question.
Uh-huh.
Can you perhaps write on the board that our final is tomorrow, and then let's like turn all the way so I can like take a picture of it and send it to Zach.
That's so mean. That's so evil. Thanks. I just want to let you know, if any of you ever play a game like this with me, I will literally meet your guts for all of eternity. Okay, once we get to eternity, I might have to forgive you, but oh, once we actually attain eternity, then I will forgive you, but not until. So you'll find out you've got very big for your forgiveness.
So,
Oh my god. Yeah, actually, I'm listening.
There we go. That seems like a good place to stop.